The Lockheed Martin team approach to the SITH program is providing system security through a method of using hardware architecture resilience by design, or HARD for short. But let's back up a little bit. What is the problem that we are trying to address? The problem is computers really only do what they're instructed to do. They're very stupid in that fashion. So you can see here on the left, we've got a standard processor. It just simply executes the instructions that is handed to it without question. In our approach, we're seeking to provide an awareness of what is executing so that the processor can make some common sense judgment to decide whether that particular instruction makes sense for what it is doing at that time. In an example of how this awareness could help prevent a security breach, I'm going to go with the example of Heartbleed. Now, Heartbleed was an attack that was discovered in about 2014 where a user essentially abuses the heartbeat check on a server. So what happens is the user would send a request to the server just to make sure that the server was still out there and still responding. But what the attacker discovered is there was a mismatch between how many letters you could request back and the size of the word. There was no check between that. So in the example on the left, the processor would get the request for user Eve wanting 50 letters for the word hat. The processor doesn't know any better. It would go to memory and start with the word hat and then return 50 letters. In this particular example, it would also return some sensitive information where Bob had changed his password and what to change the password to. Now, what we're hoping to do with SITH and the HARD approach is to give that processor the awareness that 50 letters is definitely a lot more than the 3 letters that the word hat has, and report a problem to the rest of the system. Now, how does this apply to a DoD type application? So here I'm going to describe a DoD application. So this would be a electronic warfare system, radar system detecting incoming aircraft. So in this system, we've got the general processor, some memory, along with some signal processing, which takes the data from there and decides, what's coming in on the radar, and then a sensor control, which can, turn the radar to whichever particular direction it is. And of course, with any system, you need to be able to communicate with the outside world. So in a similar Heartbleed kind of attack, we have somebody from the outside requesting the 50 letters of hat, and it's coming into the processor. And in the processor, we again start with the word hat and start overflowing that buffer into the rest of memory. Now, in this case, those extra 50 letters responds back detected 2 aircraft in Sector 6. So what has occurred in this case is the hacker has been informed that the electronic warfare system has detected those aircraft. In another example, a misdirecting sort of example, I'm going to assume we've got a much more complicated, malformed message coming in through the external communication. So in this case, the word hat plus some backup and a different set of characters. So again, in this case, it starts by going into picking off the word hat, but then backs up 42 characters and overwrites something with Sector 7, which was Sector 6. The system responds by turning from Sector 6 into Sector 7. And in this simple example, the signal processing then goes through and detects no aircraft, but it still thinks it's for Sector 6. So in this particular case of a buffer overflow, the overflow has blinded the entire electronic warfare system to the aircraft's approach. Now, security is all well and good, but in the end, security has to be balanced against the impact to the actual system. For example, if we've added all sorts of extra checks to the software, so it's going to go through and do different things to make sure that nothing's happened, we've slowed down the process of the entire system. And one can imagine, even with the simple example I just gave, that if it takes 10 times as long, 100 times as long to process the incoming signals, that's just as bad as not having the system at all or having the system hacked. So performance is a big factor on what the impact of security can be. Power and area are also two major factors in any DoT type system. If you've added a second system or a third system to perform these extra checks, you're taking up more space on a potentially an aircraft. What that turns into is more fuel, more power that has to be consumed, and all of a sudden you've reduced the range of that aircraft and you've limited the availability or the effectiveness of that platform. So again, you have to balance that increase in security against what that impact will be. Now, there are also some other rather subtle ones to do with the software changes. So in other words, if somebody has found some of these problems in there, you have to go ahead and rewrite the source code to take into account what's going on in those. And rewriting the source code could potentially change the performance of the operation of the entire system. And what this means to a Department of Defense application is that system may have to be requalified. And requalification of any software is a significant effort. Also, this would be something that could come about from switching from an old compiler to a new compiler. The compiler may assemble the code differently, so again, it may change the timing, the performance of, or even the functionality of what the software is doing. So again, this is why it would have to be requalified. Another possibility is in software is we may need new tools to analyze the code or look at the code or reprocess the code. And again, depending on how elaborate these tools are, it may impact changing the source code or changing what the compiler is doing, and again, impacting the performance. Also, another subtle aspect to this is the training that's required to implement those security features in the source code. As everyone knows, it's possible to write secure code, but not everyone may have the proper training to put those features into their source code. So, again, that may impact what's going into the software, how much it costs to produce. So, these are a number of factors that we, from a Department of Defense point of view, must be weighed against the security needs of those systems. And now I'd like to give a classic example of how security would be applied to a system, an existing system. So on the far left, I have the source code for a very simple program. It declares an array X that has 4 elements in it, and then it assigns values to those 4 elements. In the assignment of the second one, the programmer has tried to assign the value 2 to the 10th element of the array X. Now, obviously 10 is quite well beyond what the array can handle, so that would be a buffer overflow right there. So a patch would be then applied to that software where the programmer goes in and changes the source code so that it is now the proper index. Instead of 10, it would be 1. Now, what this would look like in a system here on the right is those little changes in the source code are kind of highlighted by yellow. That source code would go through a compiler, which would produce the program, which would be loaded into memory, and then the processor would be executing on those instructions. So from a security point of view, what has happened here? We have patched the one thing there, and we are praying that there are no other faults. Now, I don't know if anyone has noticed this, but there is another fault here. The programmer has used the index 4 for that last one. And in computer speak, arrays start from 0, so 4 is technically past one past the end of that array. So another buffer overflow exists in this particular simple example. So here is the problem with this patch and pray approach is you may still miss things in software as you're trying to go through and do this. Well, so it's missed on the security, but let's take a look at the impact of what this approach is. It's possible that we may have reduced some performance because we've changed some of the software. In this case, it's not very likely. We haven't really changed any additional resources for this. The compiler's still the same. We haven't changed more or needed more memory or changed the processor in any way. So that's good. We have altered the source code, and as I pointed out before, that could potentially be an impact to a requalification. We haven't changed the compiler, so that's good, and we haven't changed the environment. We haven't required additional tools or new training. But overall, this particular approach has missed some of the security, which is essentially how the Scythe program got started, is to look for something better than just this patch and pray approach. So in the hard approach, we're looking to give the program a little bit more awareness of what's going on. So what does that mean? So in the case of this simple program, on the left, the processor is just looking at the bit of code and just executing that. It's missing the context. It doesn't know that the array is of a certain size. It just simply assigns that value to whatever that index is. So we're seeking to apply that awareness to the hard processor. So in other words, the context here is important. Knowing that the index should be between 0 and 3 is the crux of this awareness for this particular approach. So taking this a little bit further, so how do we provide this context to the processor? In one method, we just simply insert this context in line with the rest of the program. So again, on the far left, the program is there as it was before on the first one. And in the second column, we've inserted some additional little metadata tags that provide that awareness, that context for the following instruction. So you can see them highlighted in yellow that each one is saying from the Scythe point of view, that X array should have an index between 0 and 3. The compiler will take those metadata instructions and turn it into something that can be interpreted by the hardware. And then that hardware is going to actually make the decision as to whether the storing that value into memory is going to be okay or not. Now on the right, you can see how that's would be implemented in an actual system. We've made some changes to the source code. The compiler has to be smarter now to understand what those tags are and to make sure that they are converted into something that can run through the processor. The memory, the actual application itself has changed, so there's some little bits of additions to the program. The processor hasn't changed at all. It's still going to execute those instructions, but we're going to tap into that processor at a specific point and watch for those special metadata tags and apply those to the particular stores to see if the stores are using the right kind of index. So from a security point of view, this particular simple approach catches all of the faults of this type. Just inherently it knows that checking this awareness will catch anything that falls beyond those bounds without having to know specifically which to fix. From an impact point of view, we do have a performance reduction. We have actually inserted additional instructions into the source code. So the processor has to execute those additional instructions in order for that context to reach the tag processing. So that's definitely a negative in this case. A positive thing is we haven't really introduced a lot of extra resources. The memory is still the same. The processor hasn't changed. This tag processing, now while it's big in this figure, it's actually a fairly lightweight check that can be added on. So this is a minor additional resources to do that check out of band from the main processor. Then back to the negatives. We have altered the source code. We have altered the compiler, and we have changed the environment. So the source code, the programmer now has to be trained to know to insert these metadata tags so that the tag processor can check it. So if you didn't trust your programmer to write it correctly the first time, do you really going to trust the programmer to get the metadata tags correct as well? We've changed the compiler, and that may change some of the execution that comes out of it. Also, this is a different environment. The programmer has to know to change to this enhanced compiler in order to get that to work. So overall, this is not a particularly attractive approach. So how about another approach for getting this context to the compiler? In this particular slide, we're going to discuss the concept of separately loading that context into the tag processor. So once again, we have on the left the same source code, the same assembly. In this case, nothing has been changed because nothing has changed with the source code. But what we're going to do is produce tags that belong to those particular stores so that those can be checked. Now on the right, you can see that I have added a tag generator. So the tag generator is going to go through all of the source code and then figure out what those tags need to be for all of the different instructions. Then that tag generator is going to load those particular tags into a separate area of memory. So the program is still the same. The program gets loaded or goes through the compiler and gets loaded into memory just the same way and then is executed in the processing pipeline. Now the tag processor is going to be watching the execution, so when one of those stores shows up, it will know that it needs to get the tag for that particular instruction. It'll go to memory and pull that tag out for that particular instruction and then check to make sure that that store has got the right index and it hasn't overflowed that particular buffer. So from a security point of view, this is good. It catches all of the faults of this type without having to know that they're all there. But from an impact point of view, how does this fare? Well, it potentially can have a performance reduction. Essentially what's happened is we've used more memory, and this could potentially cause timing issues with the memory, cause a cache miss as the memory is accessed and pulled back out. As a big negative there for the memory, we've used up additional resources in the memory or added more additional resources to accommodate these additional tags. Plus side, we still have the same source code, we still have the same compiler, but we have changed the environment. We now have to make sure that we are generating these tags and loading these tags as well. So overall, this is not a particularly favored approach either. But we are evolving on how we can actually load this context and get it to this tag processor off to the side. So now I'm going to get to the derived context, which is the approach that the hard program has decided to use. Okay, once again on the left, the source code remains the same, the assembly that comes out of that is the same, and we are trying to represent deriving the context. So in those first few instructions there, if the hard pipeline is paying attention, you can see that there is some limits being issued by the actual program itself. So if I have the hard pipeline watching for that and storing that in its own little separate bit of memory, it can then use that for the stores that are used later on in this particular simple example. And so what this means is, for security, we've caught all of this particular type. We haven't had to rewrite it or find the specific ones in the source code itself. From an impact standpoint, we have not changed the performance of the main processor. The number of instructions is the same. We haven't changed the actual processing pipeline. We haven't altered the memory structure, so we're not going to change the timing of the memory. It's using minimal additional resources. The pipeline off to the side can be very lightweight. And in this case, the context needed to store it is maybe only just a few little things depending on the complexity of the pipeline we're using. Also on the plus side, we haven't changed the source code at all. We haven't had to change the compiler. The environment is the same. The programmer hasn't had to learn any new tags to use in its source code. So overall, this is, we feel, is a very attractive approach, and it's the one we've chosen to use in the HARD program. So now the next question that comes up is, how do we respond to this detection from this out-of-band pipeline? An easy one here shown on this slide is we can simply halt the entire system. So when this out-of-band pipeline detects that something is going wrong, we can just stop the clock, stop the processor from doing anything. This would be appropriate for types of applications where the loss of the information is much more critical than the loss of the service. In another type of response, we can trap that and bring that back into the main processor as an interrupt. This would let the operating system decide on how to respond to the reported attack. It could kill that thread, it could restart something, it could change the settings in the operating system. There's a number of different possibilities that can happen with trapping the report and reporting it back through an interrupt. A third type of response would be just to simply log the attempt along with some other details. This would provide some actionable intelligence that could be done. So you could be potentially, say, logging IP addresses as to where the attack is coming from, and then use that information to decide how you're going to respond to those IP addresses in the future. As a fourth example, you could also use it to trigger an external system. For example, you could use this to put other systems into a more safe state. So if we go back to a DoD example, let's say we realize that some hacker is attempting to break into a particular system, it may not be a bad idea to put the missiles on this platform into a safe state so that the hacker couldn't potentially do something to the rest of the whole system. Another example of an external trigger is simply a call for help. This could be, another communication, a warning light, something that would trigger another system to come in and help this system as it's being hacked. In the SITH program, what are we securing against? We are looking mainly at this point in time at the MITRE-defined common weakness enumerations. These are potential flaws in software and hardware that the MITRE organization has collected up and provided in a database. The ones that we're looking at right now are different categories of CWEs. And in phase 1 and phase 2, we have looked at buffer errors, permissions, privileges, and access control types of errors, information leakage kinds of attacks, resource management, and numeric errors. Currently, we are in the middle of phase 3, and we are extending those CWE categories to include cryptographic errors and code injection. The HARD program has made a lot of progress in phase 1 and phase 2. So here on this slide, I've got kind of a quick summary of where we are in phase 2 and against the different CWEs. So here I have a whole list of different HARD pipelines that we have developed in phase 1 and phase 2 and what they do. So 10 looks for return address checking, 17 is watching for stack expiration, 22 is looking at memory boundaries, and a number of different technical approaches. Now all of these are specialized to look for different errors in the different categories. So you can see that in the middle of the slide, the CWE categories, the 5 that are mentioned through phase 1 and phase 2, you can see that these different pipelines respond to different aspects of those CWEs. Now the impact, again, is very promising. Most of these pipelines, as I mentioned before, are very lightweight, and the ones that are using the derived context have no impact to the source code, compiler, or environment. So all of these are very attractive for DoD type applications. But one thing you may notice is we have a lot of them and not one single solution to all of them. So that kind of pivots into our flexibility of this particular approach. Because we're just tapping in and these are out of band, we can add or subtract these pipelines as necessary for the application itself. So we can match the security coverage needed against that impact for a particular application. So in other words, if an application isn't concerned about a specific category or type of hack, we don't have to include that in and improve the power and area of that particular pipeline for that application. And another thing about having these all separated is it makes these security analysis for the individual ones much more tractable. Instead of having a massive system with a little change forcing to go through and prove the whole thing again, we can focus in on the individual ones. So if a new one is added, you only have to look at the new pipeline is added and just analyze that as you add it in with the rest of the system. Another aspect of the flexibility of the hard approach is we're not making any major modifications to the pipeline. What this means is we can actually apply the hard approach to other processing architectures. Now, in the SITH program, we were given the target of a RISC-V processor, and we have successfully, obviously, done many of those pipelines. The measurements on the previous slide were all for the RISC-V processor. But in our own internal research and development, we have taken some of those pipelines and shown that they can be adjusted and attached to an ARM processor and work effectively there. In closing, the demand for cybersecurity from the Department of Defense is not slowing down. There's going to be continued increase in demand for security. Essentially, what's happening is isolated platforms are not as effective as groups of platforms, systems. But with more systems, that means this interconnection is potentially exposing an attack vector to these cyber hackers, which means we need to have this additional security embedded into these systems. There are many transition opportunities throughout the platforms that Lockheed Martin supports, as well as the Department of Defense in general. The hard approach, we feel, has a lot of benefits to it in adding the security with very minimal impact to the systems. The flexibility of being able to add and subtract the pipelines as necessary to custom fit a particular need means that for UAVs, we could have a very lightweight, light touch type of approach, whereas for something shipboard or underseas, we could have something much more elaborate, more power hungry, but much more aggressive. So there are lots of different possibilities where the hard and the SITH program can improve the offerings and the cybersecurity for the Department of Defense. Thank you very much for your time. I really appreciate you listening, and I welcome any questions.